So we're going to shift gears a little bit here now. We've been talking for this entire unit about EMR, but the wave nature of EMR. Diffraction, interference, that's what we did last, right? Refraction, we did that before we did diffraction and interference. Polarization, we talked about that the very first day of the unit. All these properties that support the wave nature of light. There was an experiment performed in the year 1887 by Heinrich Hertz, the same guy that was the first one to experimentally verify Maxwell's theory of electromagnetic radiation. He discovered something called the photoelectric effect, which we'll talk a little bit more about later on. But essentially, it could not be explained by the wave theory of light. Everybody that tried to explain the observations that were made in that experiment in 1887 used the wave theory of light to explain it. And everybody's explanation couldn't explain what was observed. So along comes Einstein in 1905. Einstein suggested that light can be a wave, but can also be a particle. In fact, a wave and a particle at the same time. Now that doesn't seem to make a lot of sense. How can it be a wave and a particle at the same time? Oh wait, maybe it's a wave with a particle kind of going on the wave like this. That's not what he means. Okay, it's not a surfer that's a particle riding a wave. He means it is a wave and it is a particle at the same time. It's not a wave that carries a particle. It is a wave and it is a particle. How do we visualize that? Well, we can't, because it's outside of our realm of experience. We can't visualize it. We just have to, at some level, accept the evidence that supports that wave-particle duality. It is a wave and it is a particle at the same time. Now, this particle Einstein called a photon. A photon is a particle of light, a little quantum of energy, this little bundle of energy that's like a rock. If I throw a rock, it's got a certain amount of kinetic energy. If a photon of light leaves a flashlight and goes to an observer, then that photon of light is like the rock. It's a little bundle of energy, a little packet of energy, except it's not kinetic energy, it's photon energy. A quantum of energy, a particle of light. Right now, you just have to accept this because there's no evidence whatsoever that you've heard that supports this photon theory, this particle theory of light. But it's coming. Now, if we're talking about a rock that we're throwing, that rock, that little bundle of energy that the rock has would be equal to 1/2 mv squared. But we're not talking about a rock. This photon doesn't have any mass. So we're not going to say it has kinetic energy. It doesn't have any mass. But it has an energy like a rock has an energy as it moves through the air. The energy of the photon, however, of this quantum of energy, this photon, is equal to h times f. But because f is v over lambda, or speed of light, we often give the symbol c, then we could say the energy is also hc over lambda. Now, what does E stand for? That's easy. That's the energy of the photon. Now, that can be in a couple of different units. Joules will always work for us, but you're often going to see electron volts as well. Remember what an electron volt is? 1 electron volt is 1.6 times 10 to the minus 19 joules. Talked about that in Unit 2. That conversion is on your data sheet. F is the frequency in hertz of the EMR. So when you look at this equation that Einstein came up with, E is equal to h times f, you can tell right away that he's not discounting the wave theory of light. We can't talk about a frequency of something that doesn't have a wave nature, right? It has a wave nature. He's not saying it's not a wave. He's just saying it's also a particle. It also acts like the rock. So the frequency of the wave, the frequency of the EMR, c is the speed of light, so that's 3 times 0 times 10 to the 8 meters per second. And lambda is the wavelength of the EMR, the wavelength of the light. And again, talking about a wavelength, we've got to be talking about a wave, but we're also talking about a particle. H is a constant. Constant that we call Planck's constant. The value of Planck's constant is 6.63 times 10 to the minus 34 joules seconds. Not joules per second, joules times seconds. And it's equal to 4.14 times 10 to the minus 15 electron volt seconds. How can it have two values? How can the value, a constant, Planck's constant, have two different values? Well, what's the speed limit on the highway? 110 kilometers per hour. Or it's 30 meters per second, right? Which is it? 110 or is it 30? It's the same thing, right? Just because we're dealing with different units doesn't mean it's not the same thing. That's exactly what we've got here, right? 6.63 joule seconds, 4.14 electron volt seconds. It's exactly the same thing. It's just two different sets of units, like the kilometers per hour and the meters per second is a speed limit on the highway. Which one should we use? Whichever one's consistent with the question, right? If we're using the energy, if we're giving the energy in joules, then let's use this one. If we're doing the energy in electron volts, then let's do this one. Now, here's a rule of thumb. Okay, if you're unsure which one you should use, because there are times when you have to use joules. If you're unsure, just use joules. That might mean an extra conversion. Okay, it might mean you have to convert when you didn't really have to. But you'll never go wrong that way. Okay? If in doubt, go joules. You'll see some situations as we go on through the next couple of days where you have to use joules, in some situations where we don't have to, but maybe we do that anyway. Yep. No, on your data sheet, they're both given to you. Yeah. If you check the left-hand side of your data sheet, it is it's the second to last constant, and you've got both of those values, 6.63 and 4.14. So whatever is convenient for you. Say whatever is convenient for you. Here's an easy question. How much energy is carried by a photon of red light of wavelength 600 nanometers? Well, we want to draw attention to this because it's nanometers, right? That's going to be a wavelength. We could use HF, but we could also use HC over lambda. Both of those are on my data sheet. What value of Planck's constant do you want to use here? 6.63 or 4.14? Doesn't really say, does it, whether we should be using joules or electron volts. Pick whatever you want. If in doubt, go with joules. 6.63 times 10 to the minus 34 joules seconds. Multiply that by 3 times 58. And divide that by 600 times 10 to the minus 9. Notice again, I didn't move the decimal. I could have made it 6 times 10 to the minus 7. I didn't want to bother going through that. I didn't want to increase my chances of making a silly mistake. I just tacked on to 10 to the minus 9 on the end of it. Thank you. 3.315 times 10 to the minus 19. And what would the units for that be? Joules, because we use joule seconds. Let's round that to 3.32 times 10 to the minus 19. If we had wanted electron volts, then listen, just use 4.14. Would have got it for us. Okay, we're going to do another example here. The questions that go on page 706, the 3 questions, they're pretty quick. They're going to be for homework tonight, okay? Let's take a look at 707. Your eye can detect as few as 500 photons of light. So basically what this question is saying is that if 200 photons of light strike your eye, you're not going to detect it because it's not enough energy. Basically, it's still going to look black to you because it's not sufficient energy to activate whatever it has to activate. You know, I don't know the biology of it, but we can't see 200 photons. We can see 500 photons. The eye is most sensitive to light having a wavelength of 510 nanometers. What's the minimum amount of light energy that your eye can detect? Let's get the energy for one of these photons that we can detect. What do you want to go, electron volts or joules? Let's go joules again. If in doubt, go joules. .9, can you keep going there? Exactly. Okay, thank you. 3.9 times 10 to the minus 19. Thank you. And that's going to be in joules, right? Because we got to be consistent. My answer? What do I got to do here, Logan? Yeah, that's good. That's exactly right. That's the energy for one photon. So what do I got to do? Right. That's the energy for one photon always. So let's multiply by 500. So if our eyes are exposed to an energy less than 1.95 times 10 to the minus 16 joules, we don't detect it. More than that, we do detect it. Good? Okay, what's your homework tonight? Page 706 and page 707. Page 706 and 707. In addition, we have that little lab that we did on Thursday, was it? Wednesday, was it? No, it was Thursday. Yeah, it was Thursday. It's also due tomorrow. That's it.